Welcome to this session. So the power generation session is organized by Belsim in collaboration with TrueNorth, so our trusted partners from the United States. And today we have Frank and Derek that will share their experience with us, experience that has been well acquired over decades of work in the field.
Years ago, we hooked up with Belsim. We saw the value of data reconciliation, and so we've been working with them ever since to try to bring this technology over to the United States and get it implemented in power stations, both nuclear and fossil. So here's kind of a rundown. 2015 was the very first, I'll call it, study that was done for DVR. A few years before that, we did a lot of research, figured out how it worked, actually built the calculation ourselves, kind of a rudimentary calculation to check it out. And then we said, yeah, this is good stuff. So we started working in 2015. We started working with EPRI, and we did a study for power recovery at a power plant. In 2016, we actually wrote a guidance for using DVR for EPRI. And then 2017 to 18, we did various studies with EPRI, both in nuclear and fossil. And then we also did various studies at power stations to sort of prove the product to them. This would be nuclear, combined cycle, and fossil. In 2019 is our first implementation of DVR with Exelon, the fleet of plants at Exelon, 21 units. And so that was sort of the kickoff, kind of a big kickoff for DVR in the United States with that large utility. In 2020, we implemented Duke, their fleet of nuclear power plants. Also in 2020, we started doing power recovery, and I'll talk a little bit more about that as we go along here. And in 2021, we completed a topical report and submitted it to the NRC through EPRI for using DVR as a way to correct core thermal power and to increase power output by reducing the uncertainty of core thermal power. So that's normally done with instrumentation, and we're suggesting to the NRC that it can be done with DVR. Also, a couple of important things that happened this year was the establishment of a couple of committees in ASME. One of those committees is looking directly at DVR to add it to the power test code as a way to monitor plants and test plants. Also, there's another committee that's been established, the heat rate committee, and that heat rate committee is looking at other things, how to come up with combined heat rate for power plants, but also using DVR to help with that process. So power recovery using DVR, this is kind of where it's being applied right now in the United States with success. We use feedwater flow measurement devices in general to measure our flow for a power calculation, and often that they fail where they indicate a higher flow than you actually have. And so what we use DVR for is to identify that error in the feed flow nozzle and then put a correction in for that so that we can increase power, get a more accurate calculation of core thermal power, and thereby increasing power. So from a power recovery perspective, we've implemented it at a couple of 3 plants right now. The first one was sort of the poster child for fouling of a nozzle, and that was Clinton, and then we gained about 13 megawatts with that. Quad Cities Unit 1 and 2, each one was a little around 3 to 4 megawatts, and we are in progress of implementing power recovery at Now Mile Point Unit 1 and Unit 2. So some of the EPRI studies from the fossil point of view in combined cycle plants, there's, especially with the advent of some of the clean energy legislation that's coming out, there's been a desire to try to understand the heat rate of plants. Also, a desire to try to improve the monitoring of plants. A lot of fossil plants in particular, the instrumentation is not in very good shape. It's very old. They don't spend a lot of money to maintain it sometimes. It depends on the plant, actually. So we did some studies to try to compare what the plant's normal process for monitoring their plant performance. Looking at controllable parameters, which are basically loss calculations for all the different indicators for the plant, and then we tried to identify some of these benefits. So this is a comparison from one study that we did where we were looking at the overall plant, trying to determine what the raw heat rate value would have been and what the DVR, the reconciled heat rate value. And so you can look down here under gross turbine cycle heat rate, in this one particular plant, the raw value came in at 79.48, the reconciled value at 80.77. Now the import of this is like from a dispatching point of view, a dispatcher wants to dispatch the plant that's more economical. And so if you're dispatching the plant based on the raw data, the heat rate's better than it is with the DVR. So you may be dispatching that plant too soon as compared to another unit. So that's the importance of this kind of thing from that. Also, an understanding of that heat rate. If we were looking on the environmental side of things, the heat rate of the plant is an indicator of how much carbon is being released. And so you can see there would also be an error based on that. So the other issue that we're looking at is uncertainty of that heat rate. So not only is there a potential bias in the heat rate, but there also is, of course, the uncertainty value that you want to know. And so we were able to do some studies with plants based on, this is a different plant, but based on raw data. And you can see that your standard input-output method for calculating the heat rate ended up with about a 1.45% uncertainty. When we used DVR, we were able to get that uncertainty down to about 0.47%. So, as you can see, there's some advantages here to being able to get a reduced heat rate for the plant. And also, this is part of the motivation for the ASME committee on heat rate, that if we can get this heat rate down, then they can more accurately determine the emissions that are being released. So ongoing activities in the power industry right now in the United States, of course, the NRC is reviewing the topical report, and they are, we should have RAIs probably September of this year, and we're looking at completing everything in September of next year about. Palo Verde, we're getting ready to implement DVR there. Should start in May, which is very soon. That'll be three fairly large nuclear units. Colombia is estimated to start in July of 2021. And we're estimating to start with China, implementing at one of their plants, the CNMP, will be in May of 2021 as well. So, the future, we've had a lot of talk today about future. We're looking at online applications, kind of mixing it with what we call TSM Enterprise for alarming and work control and other types of functions like that to aid in, fixing things that you identify as wrong. And also we're looking at online performance of surveillance testing, reducing preventative maintenance. There's some DOE studies to use DVR as a digital twin. We heard that mentioned a little bit today. We're combining DVR and simulation software for advanced problem solving, and looking at replacing obsolete plant instrumentation. This would be some of the flow measurement devices that are getting very, very expensive and getting very, very obsolete. So, of course, as we mentioned, the margin uncertainty recapture. So that's kind of a 15-minute rundown of what we're doing in the United States with DVR.
So Frank, in the meantime, I will start with one question. So are there a certain type of measurements that are getting larger corrections when you apply the DVR technique in one of these nuclear power plants?
So yeah, you mean generic type of instruments? I would say that the larger corrections are going to be in flow. Sometimes you'll see some fairly large corrections in temperature. You know, if there's a instrument that's installed close to a tube sheet, like maybe condenser outlet temperature, feed water outlet temperature that's too close to the nozzle. Oftentimes you'll get some pretty big corrections on those types of temperatures. Also on the primary side, you may see some fairly large corrections on the reactor coolant loop hot legs, because oftentimes there's stratification on those hot legs. A lot of it, flow, generally speaking, is a very difficult thing to measure. And obviously, based on the power recovery discussion that I briefly had, there have been flow errors up to like 5%. We're dealing with a flow error right now at one particular power plant that's on the order of like 9%. So obviously that's a pretty large error. And we identified a pretty significant error at a combined cycle plant of their flow measurement, and it was related to the vendor supplied constituents for the gas, which is obviously used to come up with mass flow, because you need to know this ultimately the specific volume, and because of the error of the information supplied for the content of the gas for the natural gas, they ended up with like a 5 to 10% error in their flow that we identified with DVR, and they were able to correct.
That's interesting. So I suppose that everything is translated at the end in money.
Yes.
Right?
Yes.
So what can be done in a DVR model for a power plant to help add redundancy for instruments that do not have this or enough redundancy? Did you have this kind of problems?
Yeah, so we do. I think Pedro ought to jump in on this too as well. I'll start out the game. Obviously you're a slave to the instrumentation that you have, and one way you can try to achieve more redundancy in the models is to add physical relationships, because there's two forms of redundancy, right? There's basically hardware redundancy, where you have multiple measurements of the same thing. And then there's going to be functional redundancy, which is where you're connecting things through physical relationships, physics, like
correlations.
Yeah. So across a feed water heater, you might add a heat transfer coefficient or something like that. So now you can relate the extraction pressure to the outlet temperature and those kinds of things. You might add some information on the turbine, bowl coefficient, something like that, on the turbine stages to add redundancy that way. So that's probably the primary methodology for adding redundancy is going to be to look at the cycle and add these physical relationships so you can increase the redundancy there. I mean, sometimes, depending on the particular plant, if we're doing an installation, we might actually ask them to install instruments to increase redundancy, especially if it's not a significant modification to the plant. They can tee off of a pressure measurement and add another pressure measurement, something like that. So I don't know, Pedro, do you have anything to say about that?
I think you pretty much covered it. I think the need for additional instrumentation is usually to reduce the reliance on assumptions, because basically whenever you absolutely need some missing piece of information, you will be sometimes obliged to use assumptions, and some of these assumptions you're comfortable with, and some of the assumptions you hesitate because you have some doubts on whether or not they represent an added value over the instrumentation. So it's always, you don't want to be reconciling too many assumptions, giving more weight to the assumptions than you do to the actual plant measurements. So in the end, it's making sure that you have a good result that is representative. Ends up being a compromise or a balance between two contributions: the contribution of the theory and the model and the equipment parameters and constraints, and plant measurements. And you don't want to overfavor to favor one over the other too much.
Yeah, actually, I'm glad
typically these proposals about necessary instrumentation are, especially for older plants, as part of a pre-DVR implementation feasibility study, or if you don't go straight away into an online model or an online calculation, and you use DVR to make a study for a few particular data sets, during which you will make recommendations, identify the areas of the cycle where you have a lack of information, or even if you do have enough information where you don't have as much redundancy as you would like. And from there, you can say, by putting an instrument there, the core power calculation would be benefited by this much or by that much. And that's let's say the beauty of using a DVR model for doing this kind of analysis, is you can immediately translate the addition of an instrument and see what the impact is on the variables that you actually care about, or if it just has a secondary influence on locally, but not on the main variables that you care about reconciling more accurately, because basically perhaps you will gain a lot of local redundancy for some particular subsystem in the cycle, in the plant, but overall that will not translate to a big gain in the core power.
I might add to that the fact that in some cases you can, when you're adding redundancy, as Pedro mentioned, the more assumptions you make, the more you're getting away from the true data reconciliation.
Yeah.
And but you can put a confidence interval around that assumption, an uncertainty around that assumption in some cases. So that gives you the ability to, while you could add some redundancy by putting an assumption in, you can also reduce the influence of some of the assumptions by giving it, in this case, a higher uncertainty. So it's kind of a balancing act that you're trying to perform to get the most accurate model. And as Pedro mentioned, there are certain areas that we care about more than others. In the case of a nuclear power plant, reactor power being the most important for us.
Yeah, that's the general conclusion that we reached also this morning. Actually, do not estimate if you can measure. Do not assume if you can estimate.
Yes.
Right.
Yep.
More or less the same thing. So we do have a question here from Mr. Zobin. So how do you ensure convergence to the right answer? There potentially could be two different solutions. So if you want to comment something on that, I will have also some comments about DVR in general, or about how we will handle DVR.
I think this is a generic DVR question. You have a PhD, so you can answer that one.
Yeah, so in principle, what DVR in our, what our tool does, it's actually, we modify all measurements as little as possible so that all balances of the systems are closed and all constraints are satisfied. So constraints meaning, you have mass energy balances, and then you have liquid vapor equilibrium, you have reaction equilibrium, you have reactions, and so on. So that's a little bit how we arrive at the solution. So I wouldn't say correct answer, but what we deliver with reconciled data, it's actually the most probable state of the system. So, or at least, it's not the true state, because truth, we will probably never know it, but it's the most close to this truth. So it's not necessarily the correct answer. It's just by applying the technology, it's what we lead. So actually our convergence, it gives you a unique set of data, which of course can be influenced by several other parameters. But as such, we get this coherent picture of the system. So you have all the equations balanced.
So can I add something to that, Aina?
Please.
So, one of the things, this was early on when we started looking at DVR, this is one of my very, very big concerns. So it's kind of near and dear to me that you don't end up, I can push the model wherever I want to push it, so to speak. And so what we did, and we put this in some of the guidance, and we use it, is we do various sensitivity studies so we can figure out which parameters are going to push the model around, and then make sure we deal with that in the model appropriately, so that we're not having 1, 2, or whatever particular parameters shove the model around. And how we do that, part of how we do that is we look at the we'll call it the correction factor, and then we'll do these sensitivity studies and say, okay, what's this doing to it? What's this doing to it? What's this doing to it? And that does a couple things for you. It identifies those things that you need to pay attention to, and that since you know that they have a, I'll call it, inordinate effect on the model, and it also might drive you to change the model in order to lessen the influence of any one particular data point. So, and whether or not that change to the model is the uncertainty, you might increase the uncertainty or something like that, or it might be some other model change that you do. But our technique is to use sensitivity studies to identify those things that could cause the model to be moved around in a way that gives you a different answer.
Yeah, I would say that actually what we tried in the first version of the model is to give the same importance to all measurements, but these measurements will get a different importance once we tune the model. So once we do this sensitivity studies and investigated other impacts. Frank, we have another question.
Just let me add a little thing. So from an optimization point of view, when the calculation takes place and you do the optimization that leads to the overall reduction of the inconsistencies and the minimization of the corrections, this is a convex problem. So the solution for the optimization for a given objective function is unique, or should be unique. However, of course, if you change by adjusting the uncertainties on the variables, you can, as Frank said, force the model, especially if you do strong assumptions. If you force certain variables too much, you're changing the objective function and you're changing the solution slightly. But that said, the model has so much redundancy in it that unless you hit it with a hammer and really force it to go in a direction, in a particular direction, the pull to the solution, to the actual solution, is usually quite strong, and you really have to force some of the variables quite significantly, depending on the variables, of course, depending on the criticality of the variables, as Frank said. But it's not every other variable that is going to cause your model to wander into the unknown. So usually you would have to be pretty drastic, or to be touching some very specific things that you shouldn't be touching. And of course, you don't want, one of the things we look at, as Frank said, is to make sure that a particular variable is not too dependent on any individual assumption or on any individual sensor. Okay, so that's all for me. We can go to the next question if you want, Jan.
So, Mr. Zobin, if you need some more specifications, please let us know. So I will pass to the next question now. So we have, how exactly can DVR be used as digital twin? I see digital twin as a reproduction of the plant processes by mathematical models without measurements, whereas in DVR you need measurements. So how do you do DVR and digital twin relate? I can start with opening this discussion. Sometimes, what I'm always telling to my customers is that DVR can be used as a digital twin tool, because in fact, I was not aware that you do not need measurements in the digital twin, because you do need to have access to the information. And actually, what DVR or a DVR model made with VALI will give you access to detailed information on all the streams and all the equipment modeled. So to me, DVR model can be seen as a very powerful digital twin. So if you have some other opinions, please let us know. This, of course, is the opinion of the guy that works for the software provider.
So I can try to address that. So a digital twin is oftentimes a combination of measured points and simulated points, I'll call it. So like, I might have a thermodynamic model of the plant that I can compare the plant to, but I really can't compare that model to the plant accurately from a digital twin point of view unless I put, for instance, this is an example, boundary conditions in that. And the boundary conditions, of course, would be information from the plant. So, an example might be, okay, what's the digital twin going to tell me at this feed temperature or something like that? Well, you would put that feed temperature in and let the digital twin spit back at you. Okay, this is what everything should be saying. And I understand that's an overly simplistic view of the digital twin. But if you extend that into DVR, what DVR is doing is giving you a set of what we call reconciled values, okay? And those reconciled values are, in a sense, a digital twin of the measured values. And as it turns out, a more accurate representation of those measured values. So, I mean, in that sense, it's a digital twin is an often overused term. I agree nowadays, especially. And in the research that I've done on digital twins, what constitutes that digital twin is not, there's not a huge consensus on that, so to speak. Pretty much I've seen, people that use complete simulation packages call those digital twins. I've used people that would use like neural networks or something like that, call those digital twins. So I think the gambit of what the digital twin is at this point a little broad, maybe too broad, but it is a little broad. I don't know if that helps or hurts or.
Yeah, well, Frank, let's not forget that for DVR, we actually calculate all parameters of all streams.
Sure. Yeah.
So practically you do have virtual meters there where the plant do not have a physical meter.
Right, so it gives you more information than you can get from the plant, which is almost the definition of a digital twin.
Yeah, this is what me as an engineer I like very, very much. I mean, I found very interesting. So we have another question from Mr. Zobin. There are normally unidentified losses in a power plant. How does DVR take this into account? Frank, I think this would be, or Derek, that would be for you.
That's part of the modeling process, I'll call it. Let's take, for instance, something like cycle isolation, right? We would look at that cycle. We would seek to identify cycle isolation problems when we do the modeling, and then put those into the plant. So that would be like a bias that you could have due to some leakage somewhere. So that's one of the things we do is we look at that. But part of this, part of it's going to be the model is going to almost tell you sometimes that there's something wrong somewhere. The process of modeling is I build my initial model, and then you have all this stuff that doesn't make sense. And you have a lot of tags that are flagged, for instance. And so what you might do is, you'll see that could either be an instrument or it could be a component. And you could go to that component or the instrument and pursue that. So the modeling process sort of helps you with that. But and part of it has to do with, someone doing the modeling needs to understand power plants, right? You need to have the ability to be able to look, for instance, a calculated turbine efficiency and say that doesn't make any sense, or why is that so low, or things like that, or a feed water heater, for instance. There might be some sort of a parameter you'd look at on that feed water heater, and it would tell you that either the instrument's wrong or that thing's got a tube leak. And so you have to bring some intelligence into the model building process so that you can identify those things. So that's kind of how I would answer that question, David.
Okay, thank you, Frank. So we have another question from Juan Salazar. So DVR uses minimization of the correction in the meters. However, from the mathematical perspective, the full set of inequations could not lead to a local minimum. So in principle, I can probably touch this, at the first level. firstly, we have some commercially, let's say, quite powerful solvers that deal with the minimization job. So what you could have, it's that your model will not converge. So that could be one of the situations. So when you have too much indetermination in your system, or you have too many constraints, then the solvers could probably reach a local minimum, which will not be moved on. And then your model will tell you, well, I was not able to reach the 10 at -6, the typical error that we allow on the residual sum of squares. So in principle, I would say no. If the model converge, just you're not in a local minimum. If you're in a local minimum, most of the chances are that the model did not converge. If you want to add something, Todd, Frank, please.
I'd like to hear what Pedro has to say, but I mean, I agree with what you said, and you know that's it's inherent in the way the model is being, the software is calculating. So but I really like to hear is Pedro's view on that question. Can you answer that, Pedro?
Well, I'm by no means a mathematician, but since given the shape of the objective function and the convex nature of the optimization problem, it is expected, and I believe this blindly from a non-mathematical perspective, because this was what the mathematicians at Belsim have told me, is that the local minimums, there is the function has a global minimum. Any local minimum, any result that it reaches is the global minimum, and it cannot get stuck on any other points given the shape of and the way the objective function is. And how the inequations are brought into the objective function. This is basically a parable that we are looking at here. So it's a parabolic shape, so any minimum that we reach are, in principle, global minimums. What is going to change is when you change the uncertainties is that you're changing the objective function, but you don't change the overall shape. You just change basically the bending it one way or the other.
The way that you give to certain measurement over others.
Yeah, but overall, the shape of the objective function and the optimization problem should ensure that you always reach the global minimum. But I cannot give any more informed knowledge about that because I don't have the mathematical background to be able to say anything about that or explain that any further. But it's something that we can address outside, of course, this conference. If you have any doubts about that, just transmit it to us, and we will gladly address any of these questions.
So, Frank.
Yeah. So if there's no other questions, I would like to ask a question to anyone that might answer, not necessarily just the speakers. We have talked about the uprates and the uncertainty and the core power and all that. But I would like to get some feedback, perhaps, on these new implementations of DVR that are happening in the United States. What kind of results exploitation is underway right now, if any, particularly in the Exelon case? What kind of value, what kind of benefits are they pulling out of this? Is it in terms of the
I think
upgrade?
Jeff Marion's requesting mic access. Can you do that?
Oh, yeah.
So let me try to repeat the question because I just went through all that technical hardship. So the question had to do with applications for DVR at such sites as Exelon. Can you repeat the question a little bit?
No, I was just wondering because the focus of the presentation was a bit on the margin uncertainty recapture and the uprates and all that, and I was wondering if you have been already able to integrate somehow the DVR into the business process to be able to use it for maintenance purposes, for other situations other than the direct impact of the correction factors in the power uprates. You know, if it's we integrated more or less the work process of the plants?
So the answer to that is it was when I'm retired from Exelon, but it was being pursued through a couple different channels upon my retirement. In the arena of what I call advanced thermal performance, we were taking the reconciled data and integrating it with our thermal performance models. We had the caveat to be able to do that and to integrate the data. Therefore, we were able to help quantify the specific energy losses in particular areas. So that was very handy. And it was also, it gave a sense of check and balance to our processes. But we also were feeding it in through our M&D center overall, which was gathering data on the equipment level, outside of just the thermal performance or DVR type arena. And then what happens there is you see coincidental issues happening. And with that, we were able, actually every morning, the site would review the issues identified by the monitoring and diagnostics, which could have been fed through this system or by others, of course. And they were assessed, on a morning meeting basis, real time. So, and that was at all of our nuclear units. And that was very effective because, of course, not every issue that we identify is a quote unquote real issue. It could have been just something going on unrelated to a failure. But it did help identify failures, which was our goal.
So if we switch a little bit the focus to, in fact, what are the challenges of implementing the DVR in power plant, and specifically to nuclear power plants? We are in the process of collecting data for future developments. So we have some ideas in head. Let's say, I think the power generation, it's a very specific field. And we would beneficiate a lot about from getting your inputs. So what usually goes more difficult with our software? What features you would new feature you would need? So feel free to.
So I might want to just answer part of that, Frank, just from a utility point of view. I think the biggest thing to consider first is the acceptance of the technology. It was a huge deal, if you can imagine, to be a first use application in our hemisphere. So to get people to say, I believe in this technology, and to be able to convince them of that is monumental. So to do that, you have to be able to demonstrate how the model and other existing forms compare to each other. So I just wanted to introduce that, because that's a huge hurdle.
And to that end, that's why we did a lot of EPRI studies. Trying to, do the research, have it peer reviewed and hammered on, so to speak, but ultimately by the utility industry to to validate, in a sense, to justify, to demonstrate the capability of the technology. So, but again, I think that's something. I think there's a way to go still. I mean, the ASME committees looking at this is a big help. Jeff's aware of that. He's on them, and so I think we've come a long way since 2015, but I also think we have a ways to go, especially out in some sense in the fossil side of the world, the combined cycle plants, maybe the solar plants, the other renewables, those kinds of things. I really think that there's an opportunity. Anything that makes electricity can benefit from this, even a battery.
Now, I wanted to ask a little bit the opinion of the participants if they have implemented DVR. So from the data that they have till now, what will be the payback time of, or how do you call that, the when you recover your investment? If you can give us an idea, even you guys from.
So I'd just like to add something to this question from Yana. We have a few different people using DVR for a while now in this session. And of course, we have what could be considered a mature application that has been running for nearly 10 years. And we have some recent applications, in the case of Exelon, in the case of Duke.
Yeah, I think, I don't know, Adam's here, I see. I don't know if he wants to talk to this, but, there have been some, I guess, wins, I'll call it, in his use of DVR in the Duke system. And, from a cost-benefit analysis, part of the justification is based on PM reduction, calibration of instruments, those kinds of things. And then, the real cost, and also, of course, the power recoveries at Exelon. I mean, basically, when we did Clinton power recovery in the first few months, they paid for all the sites implementation of DVR. So, but the future really is people are looking at this for a broad range of things, not just quote unquote power generation. I mean, it's in power generation, but looking at using it for monitoring the primary system, so to speak, and reducing surveillance tests, that kind of stuff. And also, we're already talking to SMRs and using it, to try to save them money in the number of instruments they put in, so to speak. So, there's lots of these, there's some of the are real, they've happened, and some of them I think are in the future.
Mm-hmm. So look, you've been seeing this plenary session with AI. So in fact, why this subject has been introduced is because we are preparing for the next step. So I don't know whether for nuclear power plant it's necessarily the case, but we are looking the other sectors at this, let's say, predictive data analytics. So we want to develop a module actually in VALI that, well, not necessarily in VALI, but linked to reconcile data to look at data, at trends, and to try to predict, like condition-based maintenance and performance issues and stuff like this. So for the power generation, do you see some interest in this kind of initiative?
Well, I think that we've already been looking into this on our end anyway. I'll give it from a slimy contractor's point of view, and combining DVR with that, and then being able to automatically go to, producing work orders, producing documents to cause things to happen, that kind of stuff. That's some of the future things I was talking about, is that we're looking at, and I know at Exelon, they're looking at incorporating it with pattern recognition software, which will, now basically you're setting up your pattern recognition with better data, so to speak. So there's a combination of two different technologies being able to lead to the next point of identification of a change, so that now you can do something with that change. And then the next step is to, have some intelligence put into, I've identified a change, now what does it mean? And then what do I do with it? And you just kind of walk down the path to actually fixing whatever has changed. So that's kind of, where we're headed from that perspective. Not pure raw AI, I would say, but just combination of these different digital technologies to, solve problems and figure out how we're going to go to the next step with these problems.
Yeah, indeed, it's a little bit like this. So the AI presentation was quite broad, so we do not need to go into that much detail as presented there. we already know most of the equation governing the processes in our systems. So the pattern recognition could be guided. Let's say at least that's what we have in mind at this moment.
Sure.
Now I know that this is engineering work. Actually, all this pattern recognition, an engineer will do himself with the data. But well, we want to help the engineers. What happens is that in downstream we have very big models, so we can go to 8,000, 10,000 tags. Since everything is run together, it's a little bit difficult to follow all the phenomena that take place in such a, let's say, a refinery, for example. So with this,
so yeah, to me the biggest challenge there would be to be able to distinguish between what is actually true and meaningful results and what is just false alarms, because otherwise what we risk having is that VALI or whatever it is plugged into the other artificial intelligence models would be raising a lot of nonsense information, and we have some raised ends there, so we may need to address that too, because and that would overwhelm, it would hide all the important information. So we need to be able to filter the nonsense and the false results from the actual meritory observations, let's say, and identifications of some phenomena, some actual phenomena. We have raised them there.
So Pedro, that we are that's in our line of sight. What we're trying to do is come up with what we call intelligent alarms, and so basically we're able to develop alarming based upon as complex an equation as we want. You know, we're building that into some of the work that we're doing, taking the DVR results, putting it into a complex algorithm, and then having that filter things. A simple example of that would be something like, like alarming on a drain cooler approach temperature for a low pressure feed water heater. We put a calculation in there which has a curve that says, at this inlet temperature, this is your limit, and then you have that across the spectrum of that. So, I mean, that's a very, very simple example of some of the stuff we're working on now, but that's the goal, is to be able to not have the operators or the maintenance people chasing their tails all the time.